Good day and welcome to my YouTube channel. I am Acho Francis Deban. Today we're going to be dealing with chemistry precisely, but different topics in organic chemistry. So we're going to take selective topics in organic chemistry to analyze today. It's just to catch up with the time and ensure that we have a lot of stuff in our package. For those of you who are in medicinal chemistry, petroleum geochemistry and all that, you will find it very interesting that you will be able to assess and get information based on what you're looking for. So we're going to start with drug metabolism. First, what is a drug? A drug is a chemical substance found in the body of any human being. Probably it is foreign to the body. It being foreign means that the body does not produce it by itself or even consume it as part of its diet. So that's why we call it a foreign substance into the body. So when the body encounters a drug, it removes it through a process called drug metabolism. So for that to be fulfilled, the drug has to be broken down, modified, and be used by the body when it has been modified, or be detoxified and be removed by the body. So for drug metabolism to take place, it's having biphasic reaction, which means it's having a two-phase reaction, which is phase 1 and phase 2. But I'm going to give us a preliminary capture of what the total mechanism of drug metabolism plays before we deal with phase 1 and 2. So in drug metabolism, the parent compound here will have to react with a polar moiety or a polar metabolite, which could be a polar functional group, to give us a compound, a peculiar compound, which is a little bit polar. When that compound undergoes another reaction with a conjugating agent to make it more polar, as in soluble in the system, as such, it can be used by the body and then detoxified for the ones that is not required. You don't forget that the coupling system, which is the conjugating agent, is secreted by the body. It is an exogenous substance. Endogenous for the coupling, exogenous for the one that comes from the outside. So when we discuss the phase 1 and phase 2, you see the differences and the changes that take place therein. So we'll have a proper understanding. Now let's go back to our phase 1. In phase 1 reaction, we have like an oxidation reaction, we have a reduction, we have hydrolysis. Now oxidation in phase 1 reaction take place majorly in the liver, and the lesser extent to the kidney, the blood, the GIT, the gastrointestinal tract, and so on. So let's see how the phase 1 reaction plays. So we'll start with the oxidation reaction. Now in the oxidation reaction, we see benzene undergoing reaction with hydrolysis, to give us phenol and sometimes polyphenol. So I will show us the mechanism of that reaction. They will be able to see how it has been able to react with the metabolite, which is polar, to give us a substrate which is more polar than it was, the benzene initially, that when it undergo coupling in the conjugating side of the reaction, it will be able to be detoxified. So let's see how that goes. So we have our benzene here. Undergoes electrophilic substitution reaction to give us nitrobenzene. This nitrobenzene undergoes reduction within the presence of HCl to give us aminobenzene. The aminobenzene reacts with nitrous acid to give us benzene diazonium salt. Now, this benzene diazonium salt undergo hydrolysis to give us phenol and sometimes polyphenol. All this So this just illustrates how phase 1 reaction plays. Now, benzene itself isn't polar initially. Okay, so when it undergoes this reaction, it gives us what? Phenol, which becomes more polar than it was initially. So when we talk about drug metabolism, in phase 1, we're able to get a polar metabolite, which is this, in relation to the benzene now, which makes it polar. When it goes further reaction, which you will see in time, you see how it's going to give us something that the body can easily break for it to go out. So we're going to cut across the essential part where we talk about codeine, morphine, heroin, and see how the body can modify, or in the chemical lab, how we can elevate or activate a drug which officially wasn't that powerful to be very, very powerful through what? Drug metabolism. So let's take reduction. We're still in phase 1. We're just done with oxidation. Let's take reduction reaction of this phase 1 phase. Okay, so in reduction, number 2, reduction. In reduction, we see how 2,4,6-trinitrotoluene undergoes reaction to change it to the amino group. So let's see how that works. This is our toluene. But now we have 2, 4, 6 trinitrotoluene. 2, 4, 6 trinitrotoluene. Undergoing reduction reaction with thene in the presence of HCl to give us this. Okay. So now we are having, instead of the nitro group here becomes amino because of the reduction reaction to change the nitro to the amino group. So we have, 2 amino, 4,6-dinitrotoluene. So that is what happened. So we've talked about this. So we're going to look into hydrolysis. So how do we undergo hydrolysis? Almost in the same vein which we have played so far. We are going to see, before we go even into the protein, let's just make use of protein before we go into phase 2. So we have a protein which undergoes hydrolysis to form a different compound from what it used to be. Let's take this for example. So this is called procaine. Now, when procaine undergoes hydrolysis, H2O, what is it going to give us? We have this. This is my amino group, which is still there. And here I have the carboxyl group still facing down. Now, by hydrolysis, this is water, so it's the same thing as hydrogen hydroxide. So this is also water. So when this comes in here, we replace this bond. If I break this bond, this is going to go. Then hydrogen will replace here, and the OH will come down here. So by so doing, I'm having my OH here, plus I have the oxygen OH hydrogen group here is now coming in to take place here. When this is being cut off, I'm left with CH2, there are 2 of them, CH2 N, which is this, C2H5, there are two of that. So this is para amino benzoic acid. So we call it P amino benzoic acid plus here is 2-ethyl amino ethanol. So that's what we get, 2-ethyl amino ethanol. Now, this is the ethyl. There are C2H5 is an ethyl. There are two of them. Okay? So we either call it diethyl. I think that should go. Diethyl amino ethanol. Let's go with that. Diethyl amino ethanol. So this is the same hydrolysis taking place. We have seen how we've been able to react in a parent chain by fusing the polar metabolite in it to give us something that is more susceptible. So we're going to take the glycine conjugation in phase 2. So glycine acts as a conjugating agent with ATP coenzyme A. When we react it with a benzoic acid, we see how it gave us hippuric acid in the course of reaction. So let's see how that plays. Now we are in phase 2 reaction. One of the first reactions we're taking is the glycine conjugation. So let's see how that plays. Now this is my compound called the benzoic acid. Okay, this will react with adenosine triphosphate coenzyme A thiol. This is what will react with it. When that reaction takes place, remember, like I said, this benzene, when the reaction started initially, it just undergo the primary reaction, which is the phase 1 reaction, to give us this benzoic acid, which is more polar. So when we undergo the conjugating reaction with glycine, we'll see how it will give us a more polar compound or metabolite, which is easily excreted from the body system. The reason why the mechanism has to be two-phase is because in phase 1, it prepares the parent compound to have a moiety, which is polar, and has to undergo a second phase reaction with enzymes in the body system to make it more polar, that it can easily be excreted. Because most time when you take something which does not readily dissolve in the body system, the body will have issues with it. So for drug or any drug to be approved for anybody to take, it must have undergone the two-phase reaction, phase 1 and 2, and we must have certified it that it is okay. It can easily dissolve in the system. The body can make use of what it can, and what it cannot will be excreted or detoxified and sent out. So that is the phase reaction which we are undergoing. So this benzene has undergone the phase 1 reaction to give us this. So let's see what happened for us to undergo the second reaction. First, it has to undergo with the ATP coenzyme A thiol. Then, in the second part of the reaction, it has to react with glycine. So let's see what we get here. So when this happens, you undergo the second reaction with glycine. Glycine synthesis. So we have in the glycine COOH, CH2, and H2. So when it reacts with this, what do we get? We're going to have this. Now, this is going to go. The coenzyme A is going to go. And we are left with our nitrogen here. I'll put my hydrogen up. The carbon. Okay. CH2. C double bond O. OH. And the glycine will fuse in to make what we want. So this is hippuric acid, double P, hippuric acid, plus coenzyme A thiol, plus water as the byproduct. So this is now polar, very polar, that the body can excrete. So let's move on to another reaction of phase 2. So we're going to look at cyanide detoxification. Cyanide is a major food contaminant, especially in the tropics. It belongs to the group of drug called the cyanogenetic glucoside. So for cyanide to undergo its complete reaction, or for it to be detoxified, we know too well that cyanide is found in cassava. Now, when you eat raw cassava, it contains a high level of cyanide. And we've come across instances or situations where a whole lot of people have died because of what? Cyanide poisoning. When you take it, when it's having a whole lot of cyanide content in it, it's majorly going to kill you in the course of it, or have you hospitalized. So for this drug to be metabolized or to be broken down in the body, it has to undergo what we call the cyanide detoxification. So we have a cyanide compound reacting with a thiol. We call it thiosulfate transsulfurase. So the thiosulfate transsulfurase act as a conjugating agent, which will break down or make the cyanide or detoxify the cyanide to make it less active. So let's see what happens in that reaction. So I have my cyanide reacting with, okay, SO3. Okay, that is the thiosulfate. So we have thiocyanate plus our sulfide. Now, this cyanide is a major food contaminant, is poisonous. When you eat your cassava, naturally you should die instantaneously. But when you eat your cassava, the thiosulfate transsulfurase, which is the conjugating agent secreted by the body, interact with this cyanide to give us thiocyanate. This thiocyanate is less active. It's not that toxic, and the body can manage this, and this can easily be what is excreted. So we call this the thiocyanate. This is our cyanide. This is our thiosulfate, which acts also as an enzyme, as we call it thiosulfate. The enzyme is thiosulfate transsulfurase. So in that case, you see that cyanide, which naturally is found in cassava, in this part of the Western world, Nigeria and the nearby countries that make gari, a product obtained from cassava, as a major food component, would have been difficult, almost impossible for us to consume it, had it not been that through drug metabolism, the body is able to break down this, detoxify it into thiocyanate that the body can readily tolerate. So these are phase 2 reactions. So these become what the conjugating agent, which react with that to give us this, which the body can tolerate. So we are going to move further. We are going to look into the biological consequences of drug metabolism. Now, in biological consequences, we have seen a situation where an active drug can be made more active through drug metabolism principles. So I will show how we can make a heroin, which is an opioid, to become more active, to give us morphine, which is a tranquilizer. This is possible through what? Drug metabolism. Now let's see how we can do that. So we are looking at the biological consequences of drug metabolism. So let's take this, for example. So this is called heroin. This is it's an opioid. Let me put it this way, opioid. It's a powerful drug that should not be taken by anyone. If you take it, you know what happens. Break down your body chemistry. Let's put it that way. So this will undergo a reaction called acylation reaction. Rightfully put, deacylation. We are deacylating this. Deacylation to give us, I'm trying to manage the board now. So this is 6-hydroxy morphine. When it goes further, when this undergo oxidative deacylation, what do we get? We now have something like, I'm trying to make it small. This is called morphine. This is a morphine. So we are saying through the consequences of drug metabolism, how we've been able to turn an active drug like heroin to become more active, to give us a tranquilizer, which is morphine. So we call this intoxication. Another name for it is called intoxication reaction. Excuse me. So we're going to move on to see other cases where we can make an active drug, which is maybe a tranquilizer, to become less active, which is deactivation. All right? An active drug, which is a tranquilizer, to become less active. So let's see meprobamate, for example, what happened, what we can do with it. Now we have meprobamate. So this is meprobamate. And it's also a tranquilizer. Undergo hydroxylation to give us this. This is hydroxy meprobamate. So yeah, we have been able to move a tranquilizer which is very active to an inactive compound. So this is possible through drug metabolism. So a lot of things can be done through drug metabolism, like we will see on and on. So let's move from an inactive drug, an inactive drug to a very active drug. So we are going to take example, parathion. Parathion is an inactive drug. Then when it undergoes the drug metabolism principles with some enzymatic reaction in it, it gives us parazone, which is very active. Now, how does this work? Parathion is an insecticide. Now, parathion in itself is not poisonous, it's not toxic. Now, when it has been secreted or fluted in a room and it is being inhaled by mosquitoes or other insects, this insect, within their bodies, they secrete an enzyme that convert the parathion, which was inactive, to parazone, which becomes very active and thereby kills the insect. So the principle behind the companies who do this fleet like shelters and all that, they use this principle. They understand it, that the body of the insect possesses a certain enzyme that when it reacts with the parathion, it will convert it into parazone. And the parazone is the toxic guy that will have the insect killed. So let's see a practical example of that. This is our parathion. This is our parathion. So this is inactive. It is not active. It will undergo an enzymatic reaction in the system of the insect to give us this. So this is a parazone. So this is very active. With the conversion of this to this, it has the capacity to kill the insect instantaneously. So if we hydrolyze that, we're going to have something like this. So this is what we're going to have. So this is diethyl phosphoric acid. That's what we're going to, 1, 2, 3, 4, 5. P is 5, yeah, good. So and this is P-nitrophenol. P, para, is in the para position, so this is para-nitrophenol. So the chemistry of drug metabolism is simple. It will be able to give us or show us what we want. Like I said, that the parazone is an active compound, and so it can destroy insects instantaneously. But the parathion is a less active compound. It is not active until the enzymatic reaction takes place in the insect before it can have it destroyed. So that is about that. So that's the drug metabolism. So remember I said we're going to take selected topics in organic chemistry. So let's take something from environmental chemistry assay or assessment, which is somewhat related to petroleum geochemistry perhaps. So crude oil, over time, the pollution in this part of the world, Nigeria, you go to the Niger Delta regions where you see a whole lot of the pollution, the spillage of crude oil in our water bodies on land that makes water and land inhabitable. And this spillage is so much and it is painful how the government does not pay much attention to it. So we're going to look at the negative effect of this crude oil spillage in the water bodies, how it affects the macrofaunas, which are the little microorganisms found in the body, living things found in the water bodies, and how can we exactly know that it's actually affecting the living organisms in the water. So we use the DNA metabarcoding instrument to be able to analyze that. So generally, we say crude oil pollution is the spillage of crude oil into the water bodies, either from tankers or from drilling rigs or from oil wells, and so on and so forth, which has posed a threat to the water body. It affects the respiratory tracts of these, the water bodies of the animals, the living organisms therein, that they can't breathe no more, that leads to their death. It affects the immune system of these same water bodies or animals, organisms, or microfaunas that are in the water, that they end up being destroyed in the course of reaction. So many times we've been able to see that wherever there is oil spillage, fishes tends to die and many other things, and even goes more than that. The macrofaunas found in the water body tends to help in the breaking down or decomposition of organic matter in the water system. So if they also are being killed or destroyed, how then do we continue to harness our proper ecosystem? That becomes a problem of its own, isn't it? So this happens in the body of the water system. So we have our macrofaunas. We have example like the corals, we have the mollusks, we have the starfish, small starfish, we have the burrowing organisms like worms and all that. These macrofaunas live in the soft sediment of the water bodies, that is down the base, almost at the base of the water. They burrow, they interact with the surface of the water a whole lot, and their sizes is just 0.1 millimeter, so they are very small. And they play a role in the ecosystem, water ecosystem. They help in digestion, remineralization, even the decomposition of organic matter, many other things which they do to keep the water body in proper form. Now, how then do we know that this can be checked? We have the DNA metabarcoding instrument, which is an instrument which we call the polymerase chain reaction, that tend to multiply a lot of samples of DNA that can be cross-checked through the high throughput sequencing, which magnifies it to be seen. So summarily, what are the principles, the steps which one can use to cross-check this? Because it is through the DNA metabarcoding that we'll be able to know the macrofaunas that are being eliminated at the spot, or the macrofaunas that are resistant to the toxicity of the crude oil spillage, or we know the macrofaunas that have been extinct and those that tend to replace them, which are more resistible, okay, which are more resistant to the crude oil spillage or is dangerous because it contains a whole lot of hazard, like the polycyclic aromatic hydrocarbons, which is the PAH, and many other stuffs. So what are the simple steps? One, we collect our sample from the water body, from the base of the water body. Now, after doing that, we carry out what we call the DNA extraction. We extract the DNA of the various macrofaunas found in that sample. How is that done? We have the 3 steps. We have the lysing. We lyse it, we precipitate it, and we purify. So by lysing means we subject the cell of the DNA cell, that it would break the cell that will be able to access the nucleus and the proteins therein. After that, it is subject to precipitation. We use ethanol to precipitate it. And after that, we purify it by submerging it into water. Water have it purified in a manner that can probably be handled. Now, after this, the DNA sample is subjected to PCR, the polymerase chain reaction. The polymerase chain reaction will multiply the various DNAs of all the macrofaunas found within that sediment. All right? Within that sediment, multiply them into thousands, into millions of copies. And when these have been multiplied, we subject them into the high throughput sequencing, general high throughput sequencing, which tends to multiply the DNAs present therein that can be read by the scientists. Okay, and when this happens, we'll be able to determine to know, okay, last year, which we came to assess the DNAs of the microfaunas in this particular vicinity, we were able to find that corals were dominating. Now, 2 years after we've come back, there is no atom of coral DNA in that sample or in that environment, which means that the corals within the vicinity that oil was polluted have been extinct. Now, what was found out later, the DNAs of what we see here are more of starfish, which means the starfish were more resistant to the pollution of the crude oil. They are resistant, that's why they are there. And there could be new other microfaunas that will come to replace that. So with this instrument, the petroleum geochemists have been able to see that yes, although it's a new development that in Africa, perhaps, in the world, I think it has begun a long time ago. So we'll be able to see that through this instrument, we can analyze the samples of DNAs of various, anything we're looking for, excuse me, in peculiar areas where pollution. So that tells us the toxicity level of this oil spillage. As such, it is advisable that the government must pay proper attention to this hazard going on in our vicinity, in our environment. If you go to Uyo in Cross River State of Nigeria, you go to certain local government that have oil, you see how this spillage has caused a whole lot of havoc and danger within that place. So the living organisms therein have been endangered. You go to the Niger Delta regions, it's worse. You can't begin to imagine it. So this trend continues on and on. So until this is being put in check, we're going to have a serious problem towards that. So let us move on to another topic. How is crude oil being formed? Okay, this crude oil, everybody like in Africa, we have a whole lot of crude oil in our area. So the West have been interested in it. Actually, that is the reality. So a whole lot of people are investing in it, are spending a whole lot of millions. But how is this formed? That today the rascality involved in harnessing or exploring or drilling this oil with impunity everywhere, it's not going to last forever. We must understand how this oil is formed. Is it just going to finish? Or is it not going to finish? For how long are we going to be drilling this thing and it continue to be there? So if we know how it is formed, we should understand that for it to be formed again, this is what it to take. So in that area, we are directly into petroleum geochemistry now. So that aspect of petroleum geochemistry, the various stages of oil formation, we have the diagenesis, we have the catagenesis, and we have the metagenesis. So, but before we go into the diagenesis, there are a lot of things that take place before that. So we're going to talk about, how they call them, the organic compounds, what causes it, how do they come to play, and all that. The origin of organic compound, the origin of all these things. Let's discuss about them. We have organic matter. First of all, the organic matter are parts of the living or living things. Let's call them plant or animals. The droppings of animals, leaves and trees and all that have been deposited or been taken away from the source over time. They are called organic matter, provided they contain carbon compounds therein. Now, the origin of organic matter, before we start talking about the trees, how were they formed? Do you understand? So before we talk about how they are formed, we begin from how do various plants fix carbon 4 oxide, okay, which is the food, carbon 4 oxide. We human beings, we send out carbon 4 oxide. Carbon 4 oxide, plants takes in carbon 4 oxide as their own food to send out oxygen. So carbon 4 oxide is essential for them to grow. So how do they fix their carbon 4 oxide? There are three phases. We have the C3 pathway, which is called the Calvin cycle, okay, which is one of the process where 3-phosphoglyceric acid is being formed in the process of photosynthesis, and that 3-phosphoglyceric acid has to when it is being formed, it produces glucose and other organic compounds. So we have the C4 pathway, and also in the C4 pathway we have trees, we have example, we have maize. No, we have rice, not maize. We have sorghum and all that. These are the C4 plant, which also undergo their own process of photosynthesis to fix carbon dioxide for the trees to survive. We have the crucilation acid metabolism pathway, which we call the CAM pathway. These also have to undergo their own process. We understand that the CAM plants save water by opening their stomata in the night when the weather is cold, and closes it during the day in order to avoid water loss, that protect or save their water. So after all these plants and all these things have been formed, some on land, some on the phytoplankton on the sea, and so on. Then in the water bodies, where we understand that crude oil, the major part of crude oil is found in the water body, also it's found on land. When trees in the water body dies, there are the organic compounds now, okay? These trees die, they fall into the water body, some from land, which are the allochthonous plants, and while some from water body, which are the autochthonous, and some animals and other, when they die. In the water body, you see that the microorganisms in the water body, the fishes and all that, feed on them. The zooplankton, they feed on this organic matter, which is the dead decay of living things. They feed on them and they consume them at various levels. We have the oxic level. So at the oxic level, there is more consumption because of the whole lot of microorganisms that are aerobes. That is oxygen related. They need oxygen for their breathing. So they feed majorly on them. While these things continue to go down, they continue to scavenge them almost to the finish. Now, the wood part of it and the pellet that are stronger, that cannot be eaten by this zooplankton, go to the base of the ocean. When they get to the base of the ocean, they are heavily calcified by benthic microorganisms. This is what happened in the oxic level. In the suboxic, which happened around in the basins, we have the Black Sea, Lake Maracaibo, and so on. In this region, we move from the oxic to the suboxic, so the consumption rate of the organic matter is being reduced to a certain degree because we move from oxic to suboxic. So from the suboxic, where there is no much oxygen, the microorganisms therein are not that very much, okay? So they continue to feed on them until they are being deposited. So the deposition rate is higher than in the oxic level. In the oxic level is around 0.05 to 0.5 molecular weight. But in the suboxic, we have about 3 molecular weight. So it's higher. While in the anoxic region, where there is no oxygen at all, the deposition rate is higher because technically the organic component of the food and thereabout that comes into the water, only little microorganisms that survive without oxygen that are there, they eat on them, but they are at a lesser level. So there is a high level of deposition of organic matter and accumulation. So after all this organic matter has been accumulated over these years, over thousands of years, it's not something that takes place within a year or two. No. Over thousands of years. So you begin to see that the oil that has been explored here in Africa, in Nigeria to be precise, took thousands of years for it to be formed. So imagine that it is being finished. Now, let me continue with the story. So we're taking it as a story today. So when this gets to the base of the ocean, the accumulation over time causes what we call the temperature therein will increase. So within thousands of years, we have what we call the thermal alteration of this organic matter begin to take place. So that is where we come to the diagenesis. Within diagenesis, the temperature therein is less than 50 degrees. So there's no major thermal alteration that takes place there. Okay? So at that level, oil has not started coming out and all that, or being formed in the real sense of it. So the major things that happen there is the reconstitution of the insoluble organic matter into kerogen, because we say kerogen are organic matter that are insoluble in non-polar solvent, non-polar organic solvent. Okay, so the reconstitution of those insoluble organic matter into kerogen. Kerogen also plays its own role in the oil formation. We may talk about kerogen later on. Okay, so that is what happened in the phase 1 reaction, which is the diagenesis. The temperature is less than 50. But in the catagenesis, the temperature rises from 60 to almost 200. So the temperature is higher. So there is thermal alteration of organic matter within that region. When that thermal alteration happens, there will be dissolution of this organic matter that leads to the conversion of solid particles into liquid and liquid into gas. So that level, oil starts to form. We call it the oil window. So at catagenesis state, we have the formation of oil and the formation of gas at a lesser extent. So this is what happened. It takes thousands of years for this thing to come to play. Then in the metagenesis, which is the metagenetic stage, which is the last or the final stage, we have the temperature is 60 and above. So it is very high. So the major component formed therein is gas, natural gas, the carbon 4 oxide, and other carbon residue. So these are what the things that are being formed in the metagenetic stage, which is the formation of gas. And it is known, or it has been affirmed, that in the Niger Delta, because of the exploration of the oil because in metagenesis there is a greater depth, which means it goes beyond the level where oil is being formed. So it is said by one of our prof that the level of gas found in the Niger Delta tends to be far higher than oil. And we've been exploring oil all these years and still have oil. So imagine that gas is higher than oil. So you begin to see these are the 3 stages whereby oil is being formed. So even outside the water bodies, which I have given us a technical overview, but even on land, this oil can also be formed in places we call the source rocks and all that. So let us look at source rock as another subtopic under this, the one we're discussing about the formation of oil. Now, source rock are sedimentary rocks that have what we call thermal alteration takes place, and they produce or expel oil therein. They are constituted with fine-grained sand, which act as a conduit for the movement of oil. So this is what happened in source rock. So there are sedimentary rocks that have oil therein and have them expel at will. So in this source rock, we have various types of source rock. We have the effective source rock. Effective source rock is that source rock that has expelled hydrocarbons and is thermally mature. Thermally mature means that when it undergoes thermal alteration within it, hydrocarbons are being formed. When hydrocarbons are being formed, in that process there is what we call, it exerts thermal pressure, or fluid pressure better. It exerts fluid pressure within the rock that gives rise to cracks within the source rock that the oil spills out. Okay, so we say effective source rock is that source rock that has expelled hydrocarbons. It's known. and it is what thermally matured. So we have a possible source rock is a source rock whose source potential has not been determined, but it may have generated and expelled what? Hydrocarbons, and it's thermally mature then. But potential source rock, which is the third one, is that source rock that is an immature source rock and needs time. It's not thermally matured. So it is an immature what? Source rock, and it cannot generate what? Petroleum at will, because it needs thermal maturity for that to happen. So now, after this source rock mechanism, where we talk about the oil being spilled from the source rock, where does it go to? This will take us into what we call migration of oil. What is migration of oil? Migration of oil is of oil, crude oil, petroleum, hydrocarbons, whatever, is the movement of hydrocarbons from the source rock where it is being generated to a reservoir rock where we may rather later go on to explore for our usage. And this is possible through this fine-grained sand bed within it, which acts as a conduit for easy flow of the oil. Okay? So we're going to look at the various types of migration. We have the primary migration, secondary and tertiary migration. Now, in the primary migration, we say that oil is being spilled out, but within that rock, okay, there is thermal alteration that takes place there, that hydrocarbons will now be generated or being formed. And in the course of the hydrocarbons being formed, there is what we call fluid pressure is being exerted on the source rock that leads to a crack, and thereby oil spills out. It could spill from there to the surface. It could spill from there to a different new location and be to a source rock, to a reservoir rock where it will be preserved until it is being harvested. So this is primary word migration. But secondary migration is the movement from a source rock to a reservoir rock through that fine-grained sandbed. Then in tertiary migration is the movement of crude oil, hydrocarbons, petroleum, which has to do with oil and gas, from the reservoir rock to a newly formed reservoir rock, to a nearby reservoir rock, to a newly formed rock, or to even the surface. So you see, tertiary migration importantly, moves from a reservoir rock to a nearby reservoir, or to a newly formed reservoir, as the case may be, or spill to the outside, while secondary comes from a source rock where it is being produced to the reservoir. And in primary migration, it tells us how the oil is being generated through thermal alteration that leads to the formation of hydrocarbon, which exert fluid pressure in the source, in the rock, in the sedimentary rock, and thereby give a crack within the rock, and oil is being spilled out. So this is important in petroleum geochemistry, that we understand how these things works, how oil is being formed, how can we detect that oil is being formed, and the pathway in which it travels. All these things are essential. I may likely be capturing the pathway in which it is formed in maybe a new video or something else. Then we also have, like I said, in diagenesis earlier, in the formation of oil, one of the major things that take place therein is the reconstitution of the insoluble organic compounds into kerogen. So let's look a little or quickly into what is kerogen. I say kerogen is the organic matter that is insoluble in non-polar organic solvent, and also in non-oxidizing mineral acid like hydrochloric acid, hydrofluoric acid, due to the fact that it is obtained from marine, lacustrine, and heterogeneous organisms, animals, and plants. We have the 3 stages of kerogen. We have the kerogen, is it 4? Sorry, 4. We have the kerogen type 1, kerogen type 2, type 3, type 4. In Kerogen type 1. We say this takes place in the lacustrine environment. And this type 1 is oil prone. So it only the formation of oil is oil prone, nothing else. And the compounds therein, we have the cyclic hydrocarbons, we have the naphthalines and the aromatics. But in the kerogen type 2, which is from the marine environment, it has to do with oil and gas. In the oil and gas, we have the naphthalene and the aromatic compounds therein. We have the kerogen type 3, which is from some of them from land, plants formed from land, and some from phytoplankton from that have been subjected to some thermal barrier, not very depth barrier. So the type 3 has to do with the formation of gas only. So in the formation of gas, we have the PAH, polycyclic aromatic hydrocarbons, we have the paraffin wax. These are the constituents in that area. Then the kerogen type 4, which has to do with the formation of a very high oxygen to carbon ratio and low hydrogen to carbon ratio within the organic matter, in that sediment. So we have the Van Crevelen diagram where we can have that drawn. Okay, I think let's drop that quickly in the Van Crevelen diagram. Yes, in the Van Crevelen diagram where we have the oxygen carbon ratio and hydrogen, let's call it the hydrogen index, whatever it is, and we have something like this. Okay, I move to 2 and majorly 3. So here we have oil prone type 1 kerogen, oil and gas prone in the type 2 kerogen, majorly gas prone in type 3 kerogen, and type 4 we say it has a very high oxygen to carbon index and hydrogen oxygen index. So from what we've done now today, we've been able to cut across some major important topics in organic chemistry, especially the drug metabolism. How does drug work? We'll talk about the environmental chemistry, where we talk about the crude oil spillage and its danger to the aquatic animals and even the terrestrial. Yes. Through the process where we use the polymerase chain reaction in the course of that reaction, in the course of actually identifying the danger therein in that sediment. We've been able to also look at how is oil formed because of the rascality of the exploration rate today in Africa. We begin to look at how it is formed, that it takes thousands of years for that to be formed. Imagine if it is finished today. Where do you go to, or where do we go to if that is our major source of income? Okay, I think it's high time the West African government have to diversify their economy from the mono, which is oil, into many other sources where they can sustain themselves. We know a whole lot of countries in the West that doesn't have oil, and they are doing far better than the West African countries, especially my country, Nigeria, so you can see how that goes. So we've talked about the oil, we talked about the source rock, which is that sedimentary rock, that thermal alteration takes place and the formation of hydrocarbons therein, and which lead to fluid pressure and the spilling of the crude oil to the outermost part of the earth, or to moving from that to a reservoir rock, as the case may be. We've also talked about migration, how oil can be migrated from one place to another, from the source rock where it is being produced, the reservoir rock where it will be kept, and it can still move from that reservoir rock to another reservoir or a newly formed reservoir. That is the tertiary migration pattern. We've also talked about kerogen, which is the insoluble organic compound, which is insoluble, the organic matter that is insoluble in non-polar organic compounds, and is even non-oxidizing acid. So, and that is because of the information it possesses. That's the geological, geothermal, and so on. Geological, geothermal history. Okay, that happens. That is what gives rise to the rest of the reaction. So today we've done justice to the needful. What is obtainable is our ability to just go through them and be on good footing. It's just once in a while to bring to our knowledge the essentiality of what we need. And when we hold tight to these realities, especially the government of the day, the people therein that lives in, the educated ones, these realities will come to play. All right. Have a nice day. Thank you.